Newton's understanding of gravity was good enough to allow us to fly from the Earth to the moon. But it's kind of got to make you laugh to think that you can go all the way to the moon and back using something that's ultimately just an approximation.
It would make you chuckle to think that you could fly to the moon and back with just finite resources. Yet Newton understood gravity well enough to be able to travel from Earth to the moon. Our world is flawless in every way. There are models everywhere in the globe, yet some riddles are still unanswered after years of study. What causes the one-way flow of time? What is the reality? Why is gravity there? Why does traveling at the speed of light cause time to slow down? We have been interested by this question for millennia. Imagine that I told you that gravity isn't real. It was entirely produced by the human mind. That may sound unbelievable, but that's what renowned physician Brian Cox recently asserted. Let's examine the nature of gravity and the reasons behind the slowness of time in realizing its detrimental consequences. We have to look beyond Newton. What he cannot accomplish is the issue, not what he understands. The fact that Newton's theory of gravity only makes predictions about an object's motion under its own force is one of its flaws. Neither the existence of gravity nor its mechanism are explained by it. Newton understood that it only forces you to count. The fact that it is only from other is crucial. It's really stated that the sun, planets, and comets, all of nature's most exquisite creations, only function in accordance with the laws and decrees of the wise. Put otherwise, I'll provide you with the means to comprehend how things work. But don't ask me how or why. That belongs to God. The enormous cosmos we live in is full with mysteries that we have yet to solve. Some amazing phenomena pertaining to time and gravity, two essential components of our existence, are included in this list of mysteries. Imagine living in a world where time is unusual, unpredictable, and the forces that keep us anchored are not the same. This is the point at which our knowledge of time and gravity diverges from Albert Einstein's theory of relativity. The renowned Albert Einstein, whose theory of relativity opened our eyes and changed the way we understood the universe. Our knowledge of how time functions in various contexts, especially when we move at great speeds, is based on their work. It all began when Einstein postulated two crucial theories at the beginning of the 20th century: special relativity and general relativity. After its publication in 1905, the theory of special relativity altered our perception of space and time. It essentially informs us that regardless of motion, all non-accelerating observers are subject to the same set of rules of physics. Along with the well-known idea that time slows down or speeds up depending on the context, the theory also introduced the idea of social interaction. The light clock is among the most effective theories to explain time dilation. Imagine objects traveling at an amazing rate, almost the speed of light, in a spacecraft. Two mirrors in the spacecraft reflect a light beam that is perpendicular to the direction of travel. Light bounces vertically to move in a straight line, as observed from a plane. On the other hand, things seem differently to an outside observer who is not traveling with the aircraft. They followed the beam's route after seeing the fast-moving aircraft. The beam has to travel further to strike the mirror since the aircraft is in motion. The speed of light is always the same for all observers, according to the principles of physics. As a result, the beam should resemble a lengthy diagonal route. Things start to become intriguing now. Both observers within and outside the aircraft must experience the same amount of time for the beam to travel. The light takes longer to reach its destination, though, because of the lengthier travel to the outside viewer. Time dilation is the term Einstein used to describe the perceived time gap between two observers. The amount of time it takes for the observer to approach the stationary observer. Thus, in this instance, the time varies based on what you do. These trials verified the societal impact, so this is more than just a notion. Particles in particle accelerators, like the Large Hadron Collider, can, for instance, travel at almost the speed of light. Researchers need to account for the effects of time dilation in order to perform precise measurements. A universe where time is limitless and may be stretched or compressed to the strength of one's will is made possible by special relativity. It causes us to reevaluate how we normally think and realizes how much bigger than our experience the cosmos is. Proposed in 1905, Einstein's theory of special relativity revolutionized our understanding of the universe's structure, particularly with regard to time and motion. Critical theory demonstrates that, independent of velocity, all non-accelerating observers are subject to the same set of rules of physics. Let's look at the fundamentals of special relativity to have a better understanding of it. The idea that everyone experiences light traveling at the same speed, independent of velocity, is one of the cornerstones of special relativity. The speed at which light seems to travel is always the same, around 299,792,458 meters per second, regardless of your speed. This concept contradicts the common perception that motion causes us to move faster. It seems that the speed limit of the cosmos is equal to the speed of light. We think that events that happen at the same time do not happen for everyone at the same moment because of special relativity. From a different angle, what you witness happening simultaneously won't happen to someone else if two occurrences are occurring in distinct locations, and you are going towards them. This idea, which seems odd at first, contradicts how we think about time. Among the most significant and practical hypotheses is the one pertaining to time dilation. As you walk, time will either extend or slow down, as we discussed in the last section. In comparison to a stationary observer, time appears to pass more slowly while you move more quickly. The closer you go to the speed of light, the more noticeable this impact will be. Imagine you had two identical twins, one on Earth and the other traveling faster than light into space. The twins will be younger than their earthly siblings when they return. Real-time dilation is the cause of this phenomena, which is sometimes referred to as the twin paradox. The constant of the speed of light is the cause of this discrepancy. The twins saw the ticking of the clock as usual as they made their way towards it in little steps. The twin spacefaring clocks, however, seem to be slowing down to Earth watchers as they move around the globe. Length contraction is another effect of special relativity. To a stationary observer, an item moving at a fast speed seems short in the direction of motion. When objects approach the speed of light, this impact becomes more noticeable. At normal speeds, it is quite minor. E equals v/2, one of physics' most well-known equations, is a direct result of special theory of relativity. This formula demonstrates the interchangeability of mass and energy. This implies that energy and mass may be transformed into one another. Understanding this idea is crucial to comprehending how materials behave at high speeds and how energy is released during events like nuclear attacks. There is more to special relativity than meets the eye. There is information that is helpful. For instance, GPS systems depend on satellite signals being accurate. But the time dilation effect kicks in as the satellites approach us. Our navigation system will become less accurate if the impacts of specific connections are not factored into GPS computations. We are forced to reconsider how we conceive about time and space by special relativity. It demonstrates how the cosmos functions in a way that defies modernity. Time is a relative term that is impacted by movement rather than an absolute one. Two significant concepts that have been validated by numerous tests are the speed of light and the link between mass and energy. Moving on, let's discuss Albert Einstein's 1915 proposal for general relativity. This theory introduces us to the concept of gravity and shows us how the Earth's structure and gravity are related. In essence, general relativity refutes the traditional understanding of gravity as a force that depends on mass distance. Rather, it depicts gravity as spacetime's curvature. It's easier to understand than it sounds. We must consider the cosmos to be a four-dimensional object consisting of 3 dimensions of space and 1 dimension of time in order to comprehend general relativity. You may construct massive things in 4-dimensional space-time, such as planets and stars, and even bend space-time itself to accommodate them. We refer to this curvature as gravity. Consider space-time as a massive malleable construct. An item the size of the Earth would cause a break in this cloth. A ball, for example, rolls into the trenches when it is placed close to the dirt. This is comparable to what occurs when an item experiences gravity. This is only a matter of following space-time's curvature. It is not a mysterious power. A compelling explanation for the motion of celestial bodies in the solar system is offered by general relativity. It forecasts the planet's orbits with accuracy, including the elliptical route that the Earth takes around the Sun. Curved spacetime provides a more comprehensive explanation of orbital motion than the outdated theory of gravity as an attracting force. When Sir Arthur Eddington led an expedition to investigate the bending of stars due to the Sun's gravity in 1919, one of the most well-known observations of general relativity took place during the solar eclipse. According to the hypothesis, distant stars look somewhat out of position because of how the Sun's immense presence bends light from those stars' paths. The hypothesis was verified by observations made during the eclipse, which contradicted Einstein's predictions. According to special relativity, motion has an impact on time, just as gravity does. Time moves more slowly in high-gravity places than it does in weak-energy areas. This implies that your watch will run more slowly if you are standing close to a big object, like a black hole, than if you are standing farther away from the thing. The concept of the black hole, the location of the biggest challenge, was first proposed by general relativity. Nothing can escape a black hole's entry, not even light, due to its very powerful gravitational attraction. The event horizon, which denotes the edge surrounding a black hole, is the point of no return. Anything going beyond this threshold will be drawn into the black hole. The structure of the cosmos as a whole is also significantly impacted by general relativity. In order to maintain the universe's staticity, Einstein first incorporated cosmological constants into his equation. He considered the realization that the cosmos was expanding to be his worst error, though. The Big Bang hypothesis, which describes the origin of the universe, is based on the expanding universe theory, which is backed by general relativity. The presence of gravitational waves is a key component of general relativity. These are rippling effects in space-time brought on by rapidly accelerating large objects, including merging neutron stars or black holes. By directly detecting gravity waves for the first time in 2015, the Laser Interferometer Gravity Wave Observatory verified another aspect of Einstein's theory. General relativity has been put to the test several times throughout the years, and each time it has passed. This idea has been repeatedly validated by observations of gravitational waves, the bending of stars, and the actual orbits of planets. The notion that gravity is a fiction may seem startling, even paradoxical, given the way we experience gravity in our everyday lives. Nonetheless, there is always space for discussion, conjecture, and the pursuit of competing ideas in the field of physics. It is not unusual for scientists to question accepted beliefs. Several hypotheses concerning gravity contradict the conventional wisdom of this fundamental force. Their arguments center on competing ideas, some of which seek to alter or supplant our knowledge of gravity. Modified Newtonian dynamics, MOND, is another name for one of the most well-known alternative theories. It demonstrates how gravity operates differently at low acceleration than what is expected from standard Newtonian gravity. MOND argues that the behavior of galaxies does not need an appeal to darkness. Rather, MOND suggests that gravity accelerates to extremely high velocities. The primary topics of discussion in the gravity debate center on dark energy and dark matter. These enigmatic theories have been proposed to explain a number of cosmic phenomena, including the rotation and expansion of galaxies. Opponents of the standard theory of gravity contend that alternative theories adequately account for the phenomena and that dark matter and dark energy are superfluous. The idea that Einstein's theory of relativity is lacking is not shared by all experts. According to them, there could be more significant, unidentified, or potent factors at play that might alter or enhance our present comprehension of gravity. These scientists are looking at a wide range of options, including hypotheses that propose novel interactions or characteristics. It is important to note that the other idea was not given up right away. To ascertain the efficacy of these theories, the scientific community puts them through rigorous testing. Despite the fact that a number of competing ideas have received support thus far, none are thought to alter the way gravity is designed. It is crucial to stress that uncertainty and disease are significant facets of research. When pursuing knowledge, it is beneficial to challenge accepted notions and consider other options. Science is the result of inquiry and uncertainty. When the consensus of science is questioned, more research and a greater comprehension of the cosmos may result. General relativity's explanation of gravity continues to be the most significant and effective theory, despite the existence of rival and alternative theories. This is due to the fact that it is continuously put through rigorous testing and provides correct descriptions of phenomena like star bending and Earth orbits. It is challenging to modify general relativity because of its comprehensiveness and simplicity. Einstein's theory of special relativity, as we discussed, introduces the idea of time dilation, which states that the behavior of time varies with energy. Let's now investigate the practical and real-world consequences of this theory, particularly with regard to destination travel. People have long been interested in space exploration. We have aspirations of traveling to far-off planets, stars, and even galaxies. However, there are two major obstacles to traveling far beyond Earth: the size of the planet and the speed of light. The speed of light in a vacuum is the fastest speed in the cosmos, according to Einstein's hypothesis. The speed of light is the fastest thing that can travel. Because it takes a long time to reach the nearest star, even with the most modern technology, this constraint presents a significant obstacle to interstellar travel. Let's take a look at the well-known twins to better grasp what time dilation in space travel entails. Assume that one twin stays on Earth while the other travels at a speed far slower than light to a far-off star. Upon their return, the twins will discover that they have lived a shorter life than their siblings. The twins who traveled across space traveled to the future. For travelers, time is highly valuable. The amount of time dilation increases with distance traveled. Traveling to neighboring stars causes a significant time dilation effect, which may cause astronauts to age more slowly than those on Earth. Despite the fact that this seems like something out of a science fiction novel, social theory is actually to blame. Imagine a day when hefty missions are sent by humans to a neighboring star. Traveling even a small portion of the speed of light can take decades due to the distance. Time dilation will make the voyage seem shorter to the astronauts on board, but the planet they leave behind will be older. Time dilation has an impact on technology in addition to living things. For instance, in order to guarantee the accuracy and proper operation of computer systems and communications equipment on aircraft, time dilation must be adjusted. The fast-paced world of social media travel is fraught with difficulties. Individuals who operate in this capacity must take into account the consequences of prolonged seclusion, exposure to cosmic radiation, and the psychological ramifications of being cut off from Earth for extended periods of time. While space exploration to far-off stars remains a bright prospect, time dilation's impacts are already felt in day-to-day living. It depends on the precision of satellite signals to pinpoint its location, since it makes use of the Global Positioning System, GPS. Time dilation is affecting the satellites as they approach us. If social factors are not factored into GPS computations, the navigation system's accuracy will suffer significantly. Let's now investigate the idea of why time moves in a single direction. Our life and the cosmos as a whole are guided by the idea of time. Decisions made in the past, present, and future all flow from it. The core of human existence is this lonesome journey from the past to the future. Then why is there a route for time? Entropy is a notion that holds the key to understanding why time flows in a particular direction. A system's disorder or unpredictability is measured by its entropy. It has to do with the arrow of time and is a fundamental idea in physics. In other words, entropy is a measure of how much disorder or unpredictability there is in a given amount of time. The second law of thermodynamics describes the connection between entropy and the direction of time. According to this law, the overall entropy will either rise or stay the same in an isolated environment. Put otherwise, entropy does not naturally diminish, rather, it naturally tends to rise. There is entropy everywhere, and it has obvious repercussions. Consider a deck of cards that is perfectly stacked, for instance. The cards then become random and out of order if we shuffle them. The shuffled deck has a higher entropy than the initial order, which is lower. The arrow of time causes things to go from orderly to chaotic. The presence of various work hours at various life stages. At the macro level of our everyday existence, the rise in entropy is evident. By examining ice that has dissolved in water or the contents of a cup of coffee mix, we exacerbate the problem. This is a macro process that represents the one-way flow of time. The atomic and particle worlds demonstrate to us that the principles of physics are symmetrical with regard to time. This indicates that the process is inverted at the microscopic level. You won't be able to discern the difference when you play back and view the accident footage. We refer to this phenomena as time reversal symmetry. The idea of beginning circumstances gives rise to the seeming contradiction between reversibility in the microscopic world and irreversibility in the larger universe. The macroscopic universe is made up of numerous entities and their interrelationships. The arrow of time originated with the first occurrence in this intricate universe. Our brain processes information in a sequence, from previous memories to present and future expectations. This concept of a continual development of time is not exclusive to physics and the cosmos. The way we see time in the outside world is quite similar to how time actually exists. Significant concerns regarding reality are also brought up by time's one-way character. It tests our comprehension of cause and consequence and how we think. We have a tendency to view the future as limitless and the past as set in stone. These anatomical patterns influence our perceptions and conclusions. Our life is based on the fact that time exists. It contributes to our knowledge, personal development, and comprehension of the cosmos. Our world would be significantly different if time didn't exist. There won't be any results to our acts, no cause and effect to be observed. Thanks for watching another episode. While you're here, you can watch more space-related video.